So our last chapter, sort of, we're going to talk about work energy. We're also going to work in a little bit about momentum. Yep, because they're very similar. Momentum is mass times velocity. Here's your comparison. Momentum is mass times velocity. Kinetic energy is 1/2 mv squared, mass velocity squared. So they're similar in concept. So we'll talk about them together.
Is this like the whole chapters on work energy?
That's the core of it. We're also going to talk about momentum a little bit. We'll also work in a little bit of rotational motion. We'll see what kind of time we have. All right. So, so my wife asked me this morning if I'd seen the dog bowl. I said no. Man, nice typing. I said no. I didn't even know she could. I said no. I don't know why I typed NOW. No. Because there's 3 of them that are gonzo. I said no. I didn't know she could. Come on, man. Seeing the dog bowl, Gabe. Have you seen the dog bowl? Oh. Music, you're an idiot. All right. So, energy. What's our definition of energy? Well, it's the ability to work. Which poses a quandary here because our chapter is work/energy. So, yeah, energy is the ability to work. It'll make more sense if we talk about it, and I think you've been through this before. You've learned about this in Mr. Kelly's class in 6th grade, right? But the types of energy we're going to spend the most time talking about are these, otherwise known as mechanical. Okay? Kinetic energy, gravitational potential energy, and elastic potential energy. Kinetic energy is the energy of a moving object. Gravitational potential energy is the energy of height, the ability to do work if it falls, right? Like water going over a dam, etc. like that. And elastic potential energy is stored energy in a stretched object, like a spring or a... Oop, I don't like these. I just clipped my fingernail. So, a rubber band, right? Okay, that would be elastic. Those are the ones we're going to spend time talking about. You can see equations on the board for them. EPE, GPE, KE. Other types of energy, electric energy, right? Chemical potential energy, nuclear energy, heat energy, all kinds. What you looking for? Phantom rubber band. Okay. So essentially, all those things have the ability to do work. So energy in and of itself is kind of boring. The excitement, the fun stuff of energy is in energy transformations. When energy transforms from one type to the other. The 2 things that happen when energy gets transferred are work, or it can be transferred to thermal energy, which thermal energy is essentially waste energy. Okay? We'll talk a little bit about that too. So work is the one we're going to focus on. In physics, in order for work to be done, there has to be something moving. Okay? There has to be something moving for work to be done. You see the blue equation up there? Work equals force times distance. There has to be displacement. There has to be movement for work to be done. Make sense? And this force has to be in the direction of the displacement. Okay? We won't get into cross products here, or dot products, but The work has to be
No,
in.
it's in the dot routes.
No.
I like those.
Okay. The force has to be in the direction of the displacement. Okay, or some component thereof. This goes back to the little red wagon thing, where if you're pulling in this direction and it's rolling horizontally, right,
A little bit of it.
that's the force that does the work, right? That component.
I saw him too. He actually looks pretty good.
I was thinking that, but he's kind of aged.
I don't know. It's like Dave.
All right. Sounds like from the side conversations that we're getting there. All right. No, that's fine. Conservation manager. We're going to talk a little about this. Now, remember last chapter. Last chapter, we talked about this was our core equation, right? Last chapter, right? That's what we use like every. Okay. This chapter, every problem we do is going to come back to conservation of energy. The total amount of energy beforehand has to equal the total amount of energy after. That's going to be our base equation now. The total energy before has to equal the total energy after. Or what? Before there's a transformation. Okay? So, total amount of energy before has to equal total amount of energy afterwards. Okay? Now, we can't get rid of energy. We can't lose energy. But energy does seem to disappear on us, right? If you're driving down the highway at 80 miles an hour and you slam on the brakes and a deer runs across, you stop, right? Where'd that kinetic energy go? If you didn't hit the deer. Okay, you stopped. Where'd it go?
Now it's just stored.
It's stored where?
It's in the heat system,
It's
bro.
in the heat system, bro. Okay. If you were to slam on the brakes and then run out and jump out and touch your brake pads, what would happen? You'd burn yourself, right? It became heat. Well, what happens to that heat?
It's hot.
Eventually, your brakes cool down. It dissipates into the environment. Look at that Novak kid reading, right? Eventually, that heat from your brakes dissipates into the air. Warm air rises, and eventually, it dissipates out into the universe, right? Gone. So heat is wasted energy. Okay, that we can think of it that way. Now we're in Minnesota; it doesn't feel like wasted energy, but we don't have a real good way to recapture that heat, right? Heat.
So if we all go over and just crank our brakes, they'll heat up. Think about it.
All right, Bezic. All right. No, but that's the theory behind some hybrid vehicles becoming more and more common. When you apply the brakes, it actually, instead of, it does still have brakes, but it also engages a generator. So as you slow down, instead of all that energy going to heat, it recaptures it, puts it into batteries. That's some hybrids recapture. So instead of hitting the brakes and it just turns the heat and that heat dissipates into the atmosphere, it's gone. It actually recaptures it as electrical energy, stored energy, right? That the hybrid can use later on. So it's all a big cycle of energy being transferred. Okay. All right, work. In order for work to be done, there has to be a force that causes the displacement. So when we're pushing our mower, pulling your red wagon, whatever, we only count the force vector that acts in that direction. I forgot to change names on here. These notes. I must have forgot last year to change my notes too. But anyhow, you're right. Okay. So if you go into engineering, physics, beyond, you're going to hear about dot products and cross products. That's where this comes in. This would be a cross product. We're not going to do that, but I remember really loving cross products. Force times distance.
Do you want me to explain how to do dot products?
No.
We did just take a quiz on that.
Did you?
Let's see it.
One's sine, one's cosine, right? FD cosine of the angle between. You have to hurry up if we're going to finish these. Here, I'll pause this then. All right. Come here. Come on, there we go. All right, kinetic energy. Kinetic energy is the energy of motion, right? The two types of kinetic energy we're going to deal with are our standard, right, translational or linear moving in a line kinetic energy. 1/2 mass times velocity squared. 1/2 mv squared. Okay. We will also talk about, we're not going to spend a lot of time doing work on it, rotational kinetic energy. Okay. Rotational kinetic energy has very same. It has this I in it, 1/2 I. This right here is an I. I is the rotational inertia. And that omega, which looks like a W kind of, is the angular velocity, which is how fast it's spinning, right? How many rotations it's making. Okay? So both of those are kinetic energy. They have a mass and a velocity component, right? They have a mass and a velocity component. What? Like a W. Something like that. So rotational inertia, a large I means the mass is found farther from the axis, this thing it's spinning on. And a small I means the mass is found closer. And I'm going to do a little demonstration here. Bezik's going to do a little demonstration. Rotational, that's angular momentum we were talking about there. But just know we've got linear kinetic energy and rotational or angular kinetic energy. Very much related, though. And both have a mass, both have a velocity term in there. Oh, come on. Here you go. So our unit.
I'm not done yet.
Remember how our units build on themselves? Last chapter we had F equals MA. We had kilogram times meter per second squared, and we called that the Newton, right? Well, now we've got, if we take our work, right, look at that work equation, force times distance, right? That is a Newton times a meter, and we're going to call that a joule. So the joule, Joule, is a unit of work and energy, and we'll talk about that here in a little bit. Okay, why that is. Okay. So the Newton times a meter is a joule. So that's work, right? This is work. So work is joules. Well, also kinetic energy is 1/2 mass velocity squared. What's my unit of mass? Kilograms. What's my unit of velocity? Meters. And those are, well, guess what this is equal to?
A joule.
A kilogram meter per second squared times meter, right? Right? It's like a Newton times a meter, right? This is a Newton. This is a meter, so guess what? It's a joule. So my units of energy are joules, my units of work are joules. Make sense? and just in time